You ever try building a house without a blueprint? Yeah, me neither. It's a recipe for disaster, like trying to bake a cake with just flour and a dream. In the world of making things, drawings are those blueprints. They are the language we use to tell our ideas to the folks who turn them into reality. Clear communication is job one, folks. And in manufacturing, drawings are the messengers. A good drawing is like a good foreman, clear, concise, and leaves no room for guesswork. Get it wrong, and you're looking at wasted time, wasted materials, and a whole lot of frustration. Think about it. You've got a complex part, maybe for an engine or a piece of medical equipment. Every bend, every hole, every surface has to be spot on. Without a detailed drawing, you're asking for trouble. Misunderstandings happen, parts don't fit, and suddenly your project's timeline is shot. So yeah, drawings matter. They're not just some arcane technical thing. They're the foundation of good communication in manufacturing, and without them, things can get messy real fast. Now in the realm of mechanical engineering, drawings are everything. They're the Rosetta Stone to deciphering how things go together, how they move, how they function. We're talking gears, levers, pistons, the whole shebang. Without drawings, these intricate designs would just be ideas floating around in someone's head. Imagine trying to explain the complex workings of a car engine using just words. You'd be there all day, and chances are, whoever you're talking to would be lost. But put a detailed drawing in front of them, and suddenly things click. Drawings allow engineers to communicate their designs with a level of precision that words simply can't match. They show not just what something looks like, but how it's supposed to be made, down to the smallest detail. And let's not forget about revisions. Manufacturing is an iterative process. You try something, you make adjustments, you try again. Drawings provide a record of these changes, ensuring everyone's on the same page. No more, wait, you changed the design? The drawing tells the story. So, how do we use these magical drawings to actually talk to the people making our stuff? It's all about speaking their language. Manufacturers need information, and they need it presented in a way that's clear, concise, and leaves no room for ambiguity. First things first, standardization. We're not talking about stifling creativity here, but using common practices and symbols makes sure everyone's reading from the same playbook. Think of it like using proper grammar and punctuation. You can have the best ideas in the world, but if you can't communicate them effectively, they're going nowhere. Then there's the level of detail. Too little. And you're leaving the manufacturer to fill in the blanks, which is a recipe for disaster. Too much. And you risk overwhelming them with information. It's a delicate balance, like most things in life. The key is to strike a balance. Provide enough information to convey the design intent without bogging down the manufacturer with unnecessary details. It's about being clear, concise, and above all, accurate. Remember, a drawing is a contract. Get it right, and everyone wins. Let's get down to brass tacks. A good engineering drawing starts with a solid title block. This is the information hub, your table of contents for the part. It tells you everything from the part name and number to the material and who drew it. It's like the driver's license of your part. Next up, standard views. Think of this as looking at your part from different angles, front, top, side. These standardized views give a complete picture of the part's geometry, like a 3D model flattened onto paper. Now, we're not just talking pretty pictures here. Each view needs to be correctly aligned and projected, following specific rules called orthographic projection. It's like a mapmaker's secret language, ensuring that what you see on paper translates accurately to the real world. Section 5. The devil's in the details, dimensions, tolerances, and finishes. Here's where things get really important. Dimensions tell the manufacturer exactly how big each feature needs to be. We're talking lengths, widths, diameters, you name it. Each dimension needs to be clearly marked using the right units, either inches or millimeters, folks. But here's the kicker. Nothing in manufacturing is ever perfect. That's where tolerances come in. Tolerances tell the manufacturer how much variation is acceptable. It's like saying, okay, the diameter of this hole needs to be 1 inch, but I'll give you a plus or minus 5/1000ths of an inch. And then there are surface finishes. How smooth does that surface need to be? Do we need a mirror polish, or is a rough finish okay? This might seem like a small detail, but it can make a huge difference in how the part functions, especially in high-wear applications. Section 6, Material World, specifying what things are made of. You can't build a house out of playing cards, and you can't build a rocket out of cheese. The material matters. And it's not enough to just say, make it out of metal. We need to get specific. Engineering drawings need to clearly state the material type along with any relevant specifications. Are we talking stainless steel, aluminum, something more exotic? Each material has its own unique properties, and choosing the right one is crucial for the part's performance and longevity. This is where material standards come in handy. These standards, developed by organizations like ASTM International, formerly known as the American Society for Testing of Materials, provide a common language for specifying materials and their properties. It's like ordering a coffee. I'll have a grande 2-pump vanilla latte, please. Everyone knows what you're talking about. Section 7. Beyond the surface heat treatments and GD&T. Sometimes it's not just about the material itself, but how it's treated. Heat treatments can dramatically alter a material's properties, making it harder, stronger, or more ductile. Imagine taking a regular old horseshoe and turning it into a high-performance spring. Engineering drawings need to specify any required heat treatments, along with the desired outcome. This might include the specific temperature and duration of the treatment, as well as the required hardness or other mechanical properties. And then there's GD&T, or geometric dimensioning and tolerancing. This is the advanced course in the language of drawings. GD&T allows us to specify not just the size and shape of features, but also their orientation and location relative to each other. It's like saying, this hole needs to be perfectly perpendicular to that surface, within a tolerance of 0.002 of an inch. Section 8. Teamwork makes the dream work bonus, tips for collaboration. Now, even the best drawing in the world is useless if it doesn't foster good communication and collaboration. So here are a few bonus tips to make sure everyone's on the same page. Talk to the manufacturers. Don't just throw drawings over the fence. Pick up the phone, have a conversation. Understand their capabilities and limitations. Provide context. Don't just tell them what to do, explain why. What's the part's function? What are the critical features? Encourage questions. Make it clear that you're available to answer any questions they might have. Remember, communication is a two-way street. Use technology, 3D models, digital annotations, online collaboration tools. They can all help streamline communication and reduce errors. At the end of the day, it's all about working together to turn those ideas on paper into tangible reality. And that, my friends, is a beautiful thing.